Welcome to my YouTube channel. So today I will discuss basis and dimension in vector space. This is a lecture 4 of vector space. So first watch previous videos on vector space and then you have to watch this. So we will discuss today basis and dimension of a vector space. So for a basis you have to know the linear span of the vectors u1, u2 dot um. If we collect all linear combination of these vectors such that this ai belongs to a field k, then this collection is linear span of this vector u1 dot um. So this is a collection of all such linear combination. This is called linear combination of the vectors u1 into um, and all such collections of linear combination is span of that vectors. So the definition of basis: so a set S containing element u1, u2 un is said to be a basis of a vector space V if these two properties hold. That is, one, if un spans the set V, or this set u1, u2 un is a linearly independent set. Okay? So this is span the set that is a this set spans the vector space V, that is V equal to span of this vectors u1 un. Okay? And linearly independent means so there exists ai belongs to this field such that u1 plus plus an un equal to 0 will imply this ai equal to 0 for all I. Okay? So if this linear combination equal to 0 imply all constant is 0, then we say this is a linearly independent set. So if this set is satisfy this two property, that the set will span the V and it is a linearly independent set, then we say this is basis. And the dimension is number of element of the basis. So in if S is a basis of vector space V, so there is n elements in basis, so dimension of the vector space will be n. Okay? So the number of elements in a basis is the dimension of that vector space. So another definition of basis you can follow. So this set u1 u2 un is said to be a basis of vector space V if every element V of the vector space V can be represented as a linear combination of this vector u1 u2 un. So if we can write V equal to a1 u1 plus a2 u2 plus plus un an un, and we can express V as this for all V belongs to this set. So if each element of that vector space can be written as a linear combination of this set, then we can say this set is a basis. So this is another definition of basis. Okay? And the dimension, the dimension is the number of element in the basis of the vector space. If basis contains, if you can find a basis which contains n elements, that is finite number, so therefore the vector space will be said that finite dimensional vector space, and if the basis is infinite, then infinite dimensional vector space. Okay? So let us take one theorem. So this is a very important theorem. So let V be a vector space such that one basis of this V has m element and another basis has n elements, then m equal to n. So basis, if the vector space is finite dimensional, so it has a dimension, and if the dimension is n, the any basis can contain maximum exactly n elements. So if we find a basis S1 which contains m elements, and the second basis which contain n elements, then we conclude that m equal to n. This is the basis, means each element of this spans the vector space V, and this is a linearly independent, and the same case happen for this basis also. So this is a very important theorem. Let us take some example of vector space and the basis of the vector space. So first consider R2 n equal to 2. So this is a vector space. So this element of R2 can be written as in this form. So this is field. So any element a comma b can be written as this. So this is element from R2 and this is element from R2. Okay? So any element from R2 can be written as a linear combination of two elements of R2. So if we take S equal to 1 0 and 0 1. Okay? So these two elements can spans the whole R2. Let us take any element from this R2, that is a comma b, and you can take x comma y. So this can be written as x into 1 0 plus y into 0 comma 1. So any element can be represented as a linear combination of these two vectors. So therefore this and this is also a linear combination. How we find that linear combination? So take this as row and find the determinant of this matrix. So this is 1. So not 0. Not 0 implies not dependent. Okay, not dependent means linearly independent. So whenever the determinant of the matrix which is constructed by the element of this basis, so it comes out determinant not equal to 0, this means not 0, not dependent, that is linearly independent. So if we find that the determinant of this matrix is non-zero, then we can conclude that this is linearly independent. So it fulfills to be basis. So first of all, this is linearly independent set, and also this spans this vector space R2. So therefore this is a basis for this R2. So there are many bases, so which will contain exactly two elements. So therefore the dimension of this vector space R2 is 2. Okay, this is a standard basis. So this can be U1, this can be written as E2. So therefore S equal to U1 E2. So this is standard basis. So this is for R2, and if you take Rn, so the similar case will happen for Rn. Okay. So if we take Rn as a vector space, so this element look like x1 x2 dot dot xn, that is n triple, where all xi belongs to real number, that is a field. So if we write this set as e1 e2 dot dot en, here each e1 equal to 1 comma 0 0 0, that is n triple, e2 equal to 0 comma 1 0 0 0, that is 0, and similarly that is ei, so 0 ith position, this will be 1 and other will be 0. So this is ith position. Okay. Similarly en equal to 0 0, nth position, it will be 1. So this is defined as e1 e2 en. So if we can write this any element from Rn, so this is x1 x2 dot dot xn. So this can be written as x1 into u1, that is first component is 1, therefore x2 into e2, and similarly xn into en. So any element from Rn can be represented as a linear combination of these vectors. So this vector spans the vector space Rn, and you can prove that by finding determinant of this matrix which is constructed by this element taken as row 0 1. So this will be a n cross n identity matrix whose determinant will be 1, which is not equal to 0, not dependent, that is linearly independent. Therefore this will fulfill two conditions to be basis. First one is this will spans V and it will be linearly independent. Okay. So this will be the basis of Rn. So this is the standard basis. Okay, and now we take a vector space of 2 cross 2 matrix, that is M 2 cross 2. So you know this M 2 cross 2, this is a B C D, where A B C D all are from R. So this is a vector space. So to represent this, we need 4 0 1 0 0 0 0 1 0 and 0 0 0 1. So these 4 element we need to express this B plus C plus D. So any A, B, C, D of this vector space, any element in the form can be represented as a linear combination of these 4 matrices. Okay, so if we write this as E1, this as E2, this as E3, and this as E4, so you can write A E1 plus B E2 plus C E3 plus D E4. So therefore, this set containing these 4 vectors, that is U1, E2, E3, E4, this set E1, E2, E1, E2, E3 and E4. So therefore this set will span this vector space, and also this is a linear combination. So if you find, if you take this 0 0, so to find if this set is linearly independent or not, so therefore by calculating you get that A equal to 0, B equal to 0, C equal to 0, D equal to 0. So by taking this we get this quantity, that is constant is 0. So therefore this is linearly independent set. So this will fulfill to be a basis, fulfill 2 conditions to be a basis. So therefore this is the basis of this vector space. So now discuss one theorem which is related to basis. So this is very important theorem. So let B be a vector space of finite dimension n. So if dimension of vector space n is given, that is finite dimensional, then any n plus 1 or more vectors in B is linearly dependent. So basis is a linearly independent set. So as this vector space is n dimensional, so maximum n vectors can be linearly independent. More than n vectors in B will be linearly dependent. So this statement is that. And any linearly independent set which contains n elements is a basis of B. So as you know, the dimension of the vector space is n. Therefore, if you can find any linearly independent set which contains n vectors, it automatically becomes a basis of that vector space B. And any spanning set of B with n elements is a basis of B. Spanning set means this set will span the vector space B. Any vector from B can be written as a linear combination of these vectors, that is spanning set. So this is important theorem. Now we discuss very important theorem which is called as extension theorem in vector space. So let V be a vector space of a finite dimension, and let S contains U1, U2 dot UR be a linearly independent set, not basis. Linearly independent set of vectors in V. Then S is a part of a basis of B, as S is a linearly independent, so it is a basis, it is part of basis, and that can be extended to a basis of B. So finite dimensional, if this is a finite dimension n, so if V is a finite dimensional vector space of dimension n, and S is a linearly independent set which contains R elements, so this is a part of a basis. And the beauty of this theory is that this linearly independent set can be extended to a basis. So U1, U2 dot dot UR is linearly independent. So we can add up to n elements of this set and we can make it as a basis. So this set is extended to a basis. So that is the beauty. So we will use this theorem in the next lecture, and we will solve some previous year question also from basis and from this vector space. So if you are interested, please let me know. I will solve some previous year questions on the basis of your interest. So if you are interested, please let me know, comment and share with your friends. It will be very beneficial for you student guides, that is the students course with MA 101. So for you, it will be very beneficial. And also, if you are interested, I will solve some previous year question from this chapter and also from the next chapter also. So thank you very much. Share with your friends. Dhanyawad.